The finest level of detail that we'll explore is looking at the internal loadings in a single member of a structure. We can look at the internal loads at a single point anywhere in the member by simply slicing it, adding the internal reactions V, N, and M, and then solving using a free body diagram. If we repeat this process at every location along the member, we'd get a picture of how the normal shear and bending moments change with positions, and we can plot them as functions on what are called shear and moment diagrams. Depending on whether we're dealing with concentrated loads or distributed loads, there's different methods for getting these things onto the diagrams, and so this video talks about how to do distributed loads. The key is that the slope of the shear diagram is actually equal to the distributed load intensity. In other words, the slope of the shear, slope is V, so dV dx would be the slope of the shear, is equal to the load intensity, the loading function W of x. What that means is that we could integrate it. Delta V would be equal to the integral W of x dx. And I'll show you why the delta is there in a minute. Same token, turns out that the slope of the bending moment diagram is equal to the shear. The slope dm dx of the bending moment is equal to the shear V of x. So what that means is we could integrate that as well. So delta m would be equal to the integral V of x dx. And again, I'll show you why the delta is there in just a minute. The basic idea is that what that means is we can integrate the loading function to obtain the shear diagram, and then we can integrate the shear function to obtain the bending moment diagram. So let me prove it to you. Let me prove it to you here. If we were to cut a section of this beam here, which has reaction forces AY and BY holding it up, it's of length L, height H. We're going to measure X from the left end, and of course Y will still be in the vertical direction like so. We could chop off a section of this thing, and acting on that section would be sum of our distributed load as well as our reaction force AY, and we would have to now add the shear and the bending moment. Keep in mind that the equation for this line, since it's linear and it's going up from right to left, or from left to right, excuse me, would be equal to the slope, which is h over L, times the position x. And actually, when it comes to these problems, this is the hardest part, is figuring out what the equation of the line is, because you could imagine if it was sloping down, it would need some y-intercept or some vertical offset. If this were a curve, it could be even trickier. The tricky part is writing out these functions. We know that the distributed load acting over our little beam here, which is of length x, is going to be the integral of this small triangle, which has the same function, by the way, and that force is going to act at a distance x over 3 from the right-hand side. So what's this? If we called this resultant here just f, we could do the area of a triangle real quick, and we know that that would be 1/2 the base, which is x, times the height of this thing, which would be h over L times x, and that really quickly just becomes h over 2Lx squared. So if we were to do sum of forces in the y, we would see that we have AY going up, we would have F going down, and V going down on our free body diagram for our segment here. In other words, V is going to be equal to AY minus F. But we just saw that F is the integral of the loading function. In other words, it's equal to the integral from 0 to x, W of x dx, or AY minus 1/2 h over L x squared. That's v. And I think you can see now why it is that on the last slide I showed you that the integral part is equal to delta v and not v. We have to account for things like reaction loads as well. The moment works the exact same way. If we were to, let's just shrink this and move it up out of the way real quick. If we were to sum moments, switch colors on here, sorry. If we were to sum moments about the end of our beam here at x, we would have, acting clockwise, so negative ay times x. We have f acting in the clockwise or counterclockwise, so that's positive. It's f, and it's got a moment arm of x over 3, and we've drawn our moment in the positive direction. So we can solve this for m and see that m is equal to ay times x minus f times x over 3, which is equal to ay times x, and we already saw f was equal to this 1/2 business, and so minus 1 over 6 h over L x cubed. That, by the way, is just the integral of 1/2 h over L x squared, which was our shear function. So just to write that out for you real quick here, we have m is now equal to ay times x minus 1 over 6 h over L x cubed. And again, you see why we put the delta in there. We have to include the other part as well. And so we now see how delta m is equal to the integral of v of x dx. Delta v here was equal to the integral of w of x dx. Okay, so that's the proof that this works. Now let me show you how to actually do it in the most efficient way. So let's start over on this problem. What we're going to do is we're going to start by finding the reaction forces, and then we're actually just going to start at one end and work our way all the way to the other. So let's say we start at the left side. What we know is that at that left end, the shear is just equal to the support reactions. In other words, imagine taking an infinitely thin slice here, and what we would discover is that the shear is equal to Vay. And by the same token, the internal bending moment would also be equal to whatever the moment of the support reaction is. In this case, there isn't one, so it'd be 0. And then from there, we integrate. So let's try this out. What we do is we start with v of x equals 0. Again, x measured from the left. And we know it's equal to ay. From there, we can integrate. So v of x is going to be ay, and then we have the delta, right? So we just subtract the integral from 0 to x, w of x dx, and we're off to the races. Again, we know the function, and so this is just minus the integral from 0 to x of h over L x dx, which is equal to ay minus h over L x squared over 2. And that's equal to our shear function, v of x. Boom. So now we've got a shear function. Great. Do the same thing again for the moments. We're going to start at the left side where m is equal to the reaction moment. In this case, it's equal to 0. There is no reaction moment. And now we're going to start adding to that. So we'll start with the 0, and then we'll add to it the reaction moment, which looks like the integral of v of x dx. If you're wondering why I subtracted in the shear and I added in the moment, it has to do with our convention. We draw the shear when we cut off a section down, so that's a negative in terms of the y direction, but we draw the bending moment this way, and so it turned out to be clockwise. If we were working this problem from the other end, you would see that the shear now points up, and so this would be and so it'd be positive in there, and the moment points clockwise, and so it would be negative. But since we were working from the left to right, we did the other convention. We're just going to sub our function in. So we got the integral now from 0 to x of ay minus h over L x squared over 2 dx. And if you integrate that, you get ay times x minus h over L x cubed over 6. That is our moment function m of x. This distributed load. So now we have equations. All we have to do is graph them. So let's get this stuff out of the way here real quick. And drop in our guidelines again. Give ourselves a couple axes. We've got the shear function here and the moment function here, both plotted against x. The shear function starts at a value ay, and it looks like a negative parabola. Like so. Got that a little bit skewed there, sorry. Like so. And you could actually set the equation equal to 0 to find the x value where the shear goes to 0. And that's of interest because it turns out that where the shear goes to 0, you end up getting the maximum of the moment. And I've drawn this very asymmetrical. It's more like in the middle. It's not quite the middle, but it's close. The bending moment looks like a constant offset with a negative or an upside down cubic function. And so it's going to look something like this. And it's going to peak where the shear function equals 0. So that's an interesting feature. You can find the max min shear or max min bending moment by finding where it's equal to 0 on the shear. So there you have it. We integrate from one side to the other, and then we can take those functions that come out and graph them.